Hi everybody, let's do lecture 6 on work and energy. Let's get started. So what is work? Work is it's force times distance. So it involves both force on an object and the distance the object travels. So force times distance. Two things occur whenever work is done. There's an application of a force and movement of something by that force. Okay, so there's got to be a force applied and movement. So it's got to move over some distance. The unit of work is a Newton times a meter, because that's force times a distance, and that is called a joule. So a Newton meter is a joule. Okay, so if you have a tow truck here pulling this box along a certain distance, that force times distance will be the work that the tow truck does on the box. Okay, so here's some examples. So it looks like these people here are lifting up this brown bag from here to here, so they do work on it. The brown bag moved from this height to this height, so they moved it by pulling it on it with the rope with some force, and it moved a distance, whatever this dashed line is. So that involves work. Okay, if this is another situation, if this person is just holding two bags there, so he's definitely exerting a force, but there's no distance moved, so there's no work. Okay, let's do these examples here. It's twice as much work is done in lifting two loads one story versus lifting one load the same vertical distance. Because the force needed to lift twice the load is twice as much. So 2 times the mass requires 2 times the force over the same distance, twice as much work. Twice as much work is done on lifting a load 2 stories instead of 1 story. So you lift something 2 times as far, twice as much work. Okay. If you push against a stationary brick wall for several minutes, you do no work on the wall at all. Both of the above, none of the above. You do no work on the wall because the wall doesn't move. So there's a force on the wall, but no movement. So force times distance is 0. Okay. Work is done in lifting a barbell. How much work is done in lifting a barbell that is twice as heavy the same distance? So if you're comparing two situations, you lift one barbell and you lift a second barbell twice the mass, then because it's force times work is force times distance, that'll be twice as much to do twice as heavy barbell, so twice as much. Okay, you do work when pushing a cart with a constant force. If you push the cart twice as far, then the work you do is, well, we know work is force times distance. If we push with the same force twice the distance, is twice the work, so twice as much. Okay, work. Work equals force times distance. So it's force times distance. And there's a little asterisk here. Work is force times distance as long as the force is parallel to the direction in which the object moves. So the force and the distance have to be in the same direction. Okay. All right. 2 examples. Are these people doing work? So this guy is pushing on the wall here, but the wall isn't moving. That's no work. This guy is holding a box stationary. So he's definitely got a force on the box. There's no distance moved. So work is 0. Okay, let's talk about power. Power is how fast work is done. So in equation form, power is work done divided by time. So if you reduce the time interval that work is done, that's more power. If you lengthen the time interval that work is done, you lower the power. So a unit of power is a joule per second. That's a watt. That's after some guy named James Watt. So 1 joule per second is 1 watt. 1 kilowatt is 1,000 watts. Okay, so how could you increase your power? You can increase or decrease the rate at which work is done. So a worker uses more power running up the stairs than climbing the stairs slowly. I think that makes sense. Twice the power of an engine can do twice the work of one engine in the same amount of time. Okay, so if you hit the accelerator on a car, you're pumping more force, more work into the car. That's a higher rate of power. Okay, horsepower. There's a metric horsepower, 735.5 watts. It's the amount of power it takes to lift 75 kilograms against gravity 1 meter in 1 second. Okay. All right, let's check ourselves. A job can be done slowly or quickly. Both may require the same amount of work, but different amounts of energy. Well, they said the same amount of work, so that's the same energy. Momentum and impulse have nothing to do with it, so power. Okay. So what exactly is energy? Energy is what enables the object to do work. That's what energy is. Mechanical energy enables the object to do mechanical work. And there are two forms of mechanical energy, potential and kinetic energy. Okay, so here's a person pulling a bow back. When they pull the bow back, they're adding potential energy to the bow. And then when they let go, the bow adds kinetic energy to the arrow, reducing its potential energy. And we'll get into this balancing act in a few slides here. Okay, energy in general. A combination of energy and matter make up the universe. That's kind of an esoteric statement there, but energy and matter make up the universe. Energy is the mover of substances, both a thing and a process, observed when it is being transferred or being transformed. So it's either transferring between objects, or it's being transformed between kinetic and potential, and it's conserved. So energy is neither created, destroyed, it's just changed or transferred. Matter is a substance we can see, smell, and feel, and it occupies space. So energy, a property of a system that enables it to do work. And there are many types of energy. There's mechanical, that's kinetic and potential. We'll get into that in a little bit. Thermal, atomic, molecular, chemical, electronic, electric, magnetic, nuclear, and the list goes on. Kinetic energy is the energy of motion. Okay, and here's a formula for us. It's 1/2 times the mass times the speed squared. So kinetic energy is 1/2 times the mass times the speed squared. So, m is the mass of an object, and v is the speed of the object. So if an object's speed is doubled, the kinetic energy is quadrupled. Okay, so if this train, its kinetic energy is 1/2 times the mass of the train times the speed of the train. If we double the speed of the train, the kinetic energy of the train quadruples. Okay. Must a car with momentum have kinetic energy? I think the answer is yes, due to motion alone. Yes, when the motion is non-accelerated, it has to do with speed only. Yes, because speed is a scalar and velocity is a vector quantity. That's sort of irrelevant. And D, no. So it sounds like A is the best answer. Yes, due to motion alone. Okay. Kinetic energy is negative always. Well, it's 1/2 mv squared. Mass is always positive. V squared is a squared number, which is always positive. So kinetic energy is always positive. So this A is definitely wrong. Only if the motion is negative. Only if the motion is negative. Y direction? No, it's never negative. Okay. Potential energy is the energy of position. So it's the energy if you have an elastic band and you pull it back, the energy that you store in the elastic band is due to the position of the elastic band. Or if I have a cup here, if I lift the cup up, I increase its potential energy because of its position. If I lower it down, its potential energy is lowered because of its position. Okay. So here's a formula for potential energy due to gravity. So it's mass of the object times gravitational acceleration, which is 10 meters per second squared on Earth, times the height. And the height is always to a reference zero, which you get to choose. We'll do some problems with this. That's what it says down here. Note, height is a relative term. A reference point needs to be defined for every situation to measure the height from. For the reference point, h equals 0. So from that reference point that you choose, so that means h equals 0 there, that means P, potential energy, is 0 there. Okay, let's look at this. So stolen gravitational potential energy. Potential energy of 10 Newton ball is the same in all three cases because work done in elevating it is the same. Okay, so in situation A, the ball was lifted up 3 meters. In situation B, the ball moved 5 meters but was only lifted 3 meters. In situation C, it went up in a stepwise method in a complicated motion, but it only went up 3 meters. So since potential energy at the reference point down here is 0, and the potential energy here is mgh, which is mass of the ball, times g, which is 10 newtons, times 3, so that's 30 joules, is the same in each case. Potential energy is the same in each case. Doesn't matter how it got there. Okay, so let's use some gravitational potential energy. When lifting a ball to a specific height, the path of the ball does not matter, as potential energy depends on height only. So you can take any complicated path, but whatever height you end up at determines your potential energy. So the cable cars in San Francisco used gravitational potential energy to move up and down inclined planes. Okay. Potential energy is negative, always. That doesn't sound right. If height is negative here, then this will be negative, so not always. Only if the object is located at the reference point. If it's located at the reference point, then h is 0, so potential energy is 0. It's not negative there. Only if the object is located below the reference point. That sounds right. D never, that's wrong. So if we go back up here, if h is negative, PE is negative, that's below the reference point. That's a negative potential energy. Okay. Okay, the work energy theorem. Work can only go into or out of the system to change the energy of the system. Okay, so in equation form, work is equal to the delta energy total. And these are specific cases. So this is the work energy theorem here, that work is equal to delta energy total. It's always true. Okay, and if kinetic energy doesn't change, then work is equal to potential energy difference, potential energy change. And if potential energy does not change, then work is equal to the kinetic energy change. But in general, work is equal to the change in total energy of the system. Okay, let's do some questions. The work done in bringing a moving car to a stop is the force of tire friction times stopping distance. If the initial speed of the car is doubled, the stopping distance is, well, we know kinetic energy, when the speed of the car is doubled, then the kinetic energy goes up by 4. And so that means that the stopping distance is twice. The work done in bringing a car to a stop, so it can't be less, it can't be the same, it can't be twice, it's got to be 4 times, so it's got to be D, none of the above. Okay. Okay, conservation of energy. Energy cannot be created or destroyed. It may be transformed from one form into another, but the total amount of energy never changes. So here's an example. This person is at the top here with 10,000 joules of potential energy and 0 joules of kinetic energy. As they fall, the total energy stays the same, even though it's being converted from potential energy to kinetic energy in the motion. The total energy stays the same. That's conservation of energy. Okay, so watch this video with the pendulum. The professor is very confident that the ball will not hit their nose because they know conservation of energy. Okay, energy is neither created nor destroyed, but can change from one type to another. That's conservation of energy. It's not created or destroyed, but it can be changed. Okay, so let's do a free-falling body problem where the change in kinetic energy and the change in potential energy equals 0, which means that energy is neither created nor destroyed. Okay, and if we do have friction, we have to include energy lost to thermal energy due to friction. We'll talk about that. Okay, so these are equivalent ways to write conservation of energy. Change in potential energy plus change in kinetic energy plus change in potential energy is equal to 0. Or final kinetic energy minus initial kinetic energy plus final potential energy minus initial potential energy equals 0, same thing. And then we get rid of the parentheses here and rearrange, same thing. Or E total I equals E total F. They all mean the same thing here. Okay, this is a wall of text here. A machine is a thing to utilize work and energy so we can lift things with mechanical advantage. Let's get into some examples here. Okay, so we're using the fact that the work input and output are the same, but work is force times distance. So if we have an input force times distance and an output force times distance, they're the same, we can manipulate force and distance to do things we want. So let's just get into the examples here. So here's a lever. Okay, so on this side, this lever moves a longer distance than this side. And so if we wanted to use mechanical advantage here, we can push this a long distance with a small force to move this a short distance with a large force. So if we put a heavy object over here, we can lift it with this large force, by moving this end a large distance with a small force. So that's small force times large distance equals large force times small distance. We can use this to lift heavy things. Okay, let's look at a pulley. So if it's this person is pulling on this rope. So their rope force here is lifting up this block 1-to-1. Not a mechanical advantage. But here, this person is pulling on one rope, but there's many, many, many ropes attached to this 500 Newton thing. So all of these ropes tensions are contributing to a huge force. But when he pulls on it, he's going to get a small distance of movement. So his small force times the large distance, he's going to have to do it a lot, will generate a huge force over a small distance, which will slowly lift a heavy object. So it'll be moving a lot with a small force pulling the rope, and the heavy object will move slowly. And we're using the fact that the two works are the same, but we can manipulate forces and distances. Okay, here's some examples of other situations where this happens. There's an inclined plane, wheel and an axle, wedge. This is all manipulating work, and we can use force and distance to our advantage. Okay, an ideal pulley system. In an ideal pulley system, a woman lifts a 100 Newton crate by pulling a rope downward with a force of 25 newtons. For every 1 meter length of rope she pulls downward, the crate rises. Well, we know it's 100 newtons moving 1 meter. Well, she's pulling the rope 1 meter with 25 newtons, which means the 100 Newton crate has to move a quarter of that for the works to be equal. So that's 25 centimeters, which is a quarter of 1 meter. Okay. All right, efficiency. Efficiency is, well, useful energy output over total energy input. So we put energy into something we want to do, we get some useful energy out. What's that percentage? That's our efficiency. Okay, a certain machine is 30% efficient. This means that the machine will convert 30% of the energy input to useful work. That sounds good. 70% of the energy input will be wasted. That sounds right. That sounds what efficiency means. 70% of the energy input to useful work. That sounds wrong. Not both, not none. It's I think of A. Okay. All right, sources of energy. We got the sun, we got wind, nuclear, geothermal, batteries, and fuel cells. We can find sources of energy all over the place. Just by the way, the sun is a huge source of energy. Just to give you an example, read this sentence here. More energy from the sun hits the earth in 1 hour than all of the energy consumed by humans in an entire year. So the sun is powerful. Okay, recycled energy. Okay, so if we have efficiency, we have some wasted energy every time we try to do something. If we can use that wasted energy in some form, that's recycled energy. That's good. Our bodies require energy. That's why we eat. That's why our cells use that food and that energy to keep going. And so we can use our brains, and we can do lift weights and do all kinds of different things. Okay, let's do some practice problems. Example of conservation of energy. A block of ice slides down a frictionless ramp, so no energy lost due to friction. The block starts from rest. What is the speed of the block after it has reached a height of 5 meters below the initial starting point on the ramp? Okay, so this is height at 5. At this starting point, no kinetic energy. Potential energy is not 0. And at the end, potential energy is 0 because it's at the reference point. And kinetic energy is not 0. Okay, so gravitational potential energy turns into kinetic energy. Let's get some numbers here. So the total energy before is equal to the total energy after, and the initial energy is just potential energy, and the final energy is just kinetic energy. So kinetic energy final equals kinetic potential energy initial. We know the formula for that, 1/2 mv squared. We know the formula for that, mgh. And then we can cancel the m's. It gives us 1/2 at vg squared equals gh. We do some algebra, and we get v equals square root 2gh. We plug in numbers 2 and 10, and h is 5. That gives us 10 meters per second. Okay, so we could use conservation of energy to figure out what the speed will be after this block slides down the inclined plane. Okay, here's another example. A hockey puck of mass 2 kilograms slides on the ice at 3 meters per second. The puck comes to a stop after sliding for 10 meters. How much work does friction do in stopping the puck? Okay, so all the kinetic energy is lost due to friction because it initially had kinetic energy and it has no kinetic energy at the end. So all of the energy was due to work due to friction. Okay, so normally we would use work equals force times distance, but we don't know the friction force. So since we don't know the force, we have to use conservation of energy to solve the problem. So we know the original kinetic energy turns into work done by friction in stopping the puck. So the work done by friction is equal to the change in kinetic energy, and that's final kinetic energy minus initial kinetic energy, which is just minus initial kinetic energy, because this is 0. That's minus 1/2 mv squared. Plug in the numbers, we get -9 joules, and that's how much work friction did. Okay, and if we know the force acts over 10 meters, so it says right here, assume the constant friction force acts over 10 meters, we can find the force of friction. So we know the work, we can use the work is equal to force times distance. We know that the work is -9 joules. We don't know the force, that's what we want. Distance is 10. So divide by 10, we get -0.9 newtons. So that's the force of friction. And the negative sign tells us that the friction force is to the left in this picture. Okay, this velocity of the puck is to the right. We're going to call that positive. And then the friction force to the left is negative. That's where this negative sign comes from. Okay, let's do another one. A cannon shoots a cannonball of mass 10 kilograms straight up in the air with initial kinetic energy of 500 joules. Okay, what is the initial speed of the cannonball? What is the final potential energy? And neglect air resistance. So we're not going to worry about energy loss to friction here. So let's start with the first part. What is the initial speed of the cannonball? Well, we know the initial kinetic energy is 500 joules. And we know the mass is 10 kilograms. So we know the formula for kinetic energy is 1/2 mv squared. We know it's equal to 500 joules. Plug in 10 kilograms. Solve for V. So we get a 5 here. 500. 500 divided by 5 is 100. Square root of 100 is 10 meters per second. So that's the initial speed. What's the final potential energy? Since we're neglecting air resistance, the kinetic energy initially has to be equal to the potential energy final. So 500 joules. That's an easy one. Okay, let's continue. Let's instead assume that we cannot neglect air resistance, so we're going to have some loss from friction. The cannonball reaches 2 meters maximum height. How much the initial kinetic energy is lost due to thermal energy? Okay, so let's look at this picture right here. So the initial situation is there's no potential energy because it's at the bottom. The thermal energy is 0 because the air friction hasn't done any work yet. And the kinetic energy is high because the cannonball just got shot out of the cannon. Okay, at the end, the kinetic energy is 0 because at the turnaround point, at the highest point, the maximum height, it's not moving, so kinetic energy is 0. Potential energy is 200 joules. Oh, we're going to get to this in a second. And then the thermal energy we want to know. Okay, so we need to, because we only know the maximum height is 2, so we need to use this formula here to find the potential energy at the final position. So we know that potential energy is mgh. Plug in 10 and 10 and 2 with the proper units. That gives us 200 joules, and that goes over here. And since we want to find how much of the initial kinetic energy is lost due to thermal energy, we know the initial kinetic energy is 500. We know the final potential energy is 200, and the remainder should be thermal energy. So that must be 300 joules. So just to note, in the quizzes, we're not going to be doing these heavy calculation problems, but we should be able to talk about energies going up and down and comparing how does thermal energy enter into it. If you go higher, potential energy is going up. If you slow down, kinetic energy is going down. If you're at rest, kinetic energy is 0. But we're not going to be doing these big number problems. Okay, let's do one more. One more, yeah. A 2 kilogram block is pushed up a long ramp. if the block starts moving at 10 meters per second, how high up the ramp does the block reach before stopping? Okay, so this is the initial position down here. This is the final position. We want to know how high up the ramp it goes. So the initial situation is there's no potential energy because it's at the bottom. The kinetic energy is greater than 0 because it's moving at 10 meters per second. At the end, it's not moving because it's at the maximum height at the turnaround point. Speed is 0. So no kinetic energy. Potential energy is greater than 0. We're going to use this to calculate the final height. So we know kinetic energy initial is equal to potential energy final due to conservation of energy. Kinetic energy is 1/2 mv squared. PE is mgh. Cancel the m's. We get 1/2 v squared equals gh. Solve for h by dividing by g. And then plug in numbers. 1/2, 10 squared, 10 meters per second squared. And this gives us 5 meters. So how high does it go up the ramp? 5 meters. So this is 0. If this is 0 meters, this block, at the end, it's 5 meters higher than it was. And we can use kinetic energy, potential energy, and conservation of energy to find these answers. Okay, that's it for conservation of energy and work. If you have any questions, let me know, and I'll see you guys for lecture next time.